China is building the world's largest oil and gas pipeline. The engineering behind it is unlike anything you've ever seen. We're talking about a 6,200-mile energy artery that crosses mountains taller than the Rockies, deserts that reach 120 degrees Fahrenheit, and permafrost zones where the ground stays frozen year-round. Traditional pipeline technology simply does not work in these conditions. Yet China is laying pipe at speeds that seem physically impossible, using construction methods that are rewriting the rules of mega infrastructure. Here's how they are actually pulling this off. You are looking at a pipeline that will stretch from the frozen gas fields of Siberia, cut through the peaks of the Altai Mountains, cross the Taklamakan Desert, and terminate in western China. 6,200 miles of continuous steel pipe. To put that in perspective, that is like building a pipeline from New York City to London and then adding another 1,000 miles on top of it. But distance is just the beginning of the problem. This pipeline has to climb over mountain passes that sit at elevations of 13,000 feet and then drop down into desert basins below sea level. That is an elevation change of over 15,000 feet. Pipeline pressure has to handle that without rupturing the steel or creating dead zones where gas will not flow. Then there is the temperature nightmare. In the northern sections near Russia, winter temperatures plunge to minus 60 degrees Fahrenheit. The steel contracts. Welds that were perfect in summer conditions can crack apart. In the Taklamakan desert sections, summer heat hits 130 degrees Fahrenheit. The steel expands. Joints that were solid in winter can fail catastrophically. And all of this runs through earthquake zones. The Altai region experiences regular seismic activity. A traditional rigid pipeline would snap like a twig during a tremor. Western pipeline engineers looked at these combined challenges and said it could not be done with existing technology. The variables were too extreme, the terrain too hostile. China started construction anyway in 2021, but here is where the engineering gets really insane. Normal pipeline steel is strong, but it is rigid. That works fine when you are building across flat, stable ground with consistent temperatures. But this pipeline needed something that had never been manufactured at scale before. Steel that could flex during earthquakes, expand and contract through temperature swings of 190 degrees, and still maintain structural integrity under 60,000 pounds per square inch of internal pressure. The material science labs in Baotou spent 3 years developing a new alloy. They added micro amounts of vanadium and niobium to the steel mix, creating a crystalline structure that behaves almost like a metal memory foam. When stress hits the pipe, the crystal lattice deforms slightly, then returns to its original shape. It is not flexible like rubber, but it has just enough give to absorb shocks that would shatter conventional pipe. But manufacturing this alloy is brutally difficult. The temperature during the forging process has to stay within a 5-degree Fahrenheit window. Too hot, and the crystalline structure breaks down. Too cold, and the metals do not bond properly. Western steel mills could not maintain that level of precision at the production speeds required. China built 12 new forging facilities specifically for this pipeline. Each one uses AI-controlled induction furnaces that adjust heating in real time, monitoring the molecular structure of the steel as it forms. They are producing pipe sections at a rate of 200 miles of pipeline per month. That is pipe that meets specifications no Western manufacturer has ever achieved in mass production. And then came the problem nobody anticipated. You can manufacture the perfect pipe, but if you can't weld it together in the field, you've got nothing. The conditions along this route make welding nearly impossible. In the northern sections, you're working in negative 50 degrees Fahrenheit, where your welding equipment freezes solid. Your electrodes become brittle. The metal you're trying to join contracts the moment heat touches it, creating microfractures in every seam. In the desert sections, it's the opposite nightmare. Sand gets everywhere. A single grain of sand trapped in a weld creates a weak point that will fail under pressure. The heat is so extreme that welders can only work 20-minute shifts before heat exhaustion sets in, and you need every single weld to be perfect. One bad joint in a 6,200-mile pipeline and you've got a catastrophic failure waiting to happen. Traditional pipeline projects solve this with slow, methodical welding. Experienced crews take their time, inspecting every inch, but at that pace, this pipeline would take 30 years to complete. China needed to lay an average of 5 miles of pipe per day day to hit their timeline. That means completing roughly 250 welds daily, each one flawless, in conditions that make welding nearly impossible. The solution was robotic welding crawlers. These machines look like mechanical crabs that clamp onto the outside of two pipe sections. Inside, an AI-guided welding head creates a 360-degree perfect seam in under 12 minutes. The robot does not care if it is -60 degrees Fahrenheit or 130 degrees Fahrenheit outside. It adjusts arc temperature, feed rate, and shielding gas flow in real time based on environmental sensors. But the real breakthrough is what happens next. Each weld gets inspected by an ultrasonic scanner built into the crawler. It checks the molecular structure of the weld, looking for voids or inclusions smaller than a grain of rice. If it detects even a microscopic flaw, the robot grinds out that section and re-welds it on the spot. No human inspection needed. No delays. These crawlers are completing welds with a failure rate of less than 0.01%. That is 10 times better than the best human welding crews in ideal conditions. And they are doing it in an environment where human welders would fail half the time. But laying perfect pipe is meaningless if you cannot get it into the ground. You need a trench. 6,200 miles of trench, anywhere from 6 to 12 feet deep depending on the terrain. In normal soil, that is straightforward, but this pipeline crosses permafrost that has been frozen solid for 10,000 years, desert hardpan that is like digging through concrete, and mountain bedrock that requires blasting. In permafrost, the ground is so frozen that normal excavator teeth shatter on impact. The ice-soil mixture is harder than most rock. Traditional Arctic pipeline projects use thermal thawing, melting the ground with heaters before they dig. But that takes weeks per mile. At that pace, you would still be digging in 2060. China deployed excavation machines that look like they were designed for mining asteroids. These are not your standard backhoes. They are 60-ton tracked beasts with tungsten carbide cutting teeth that rotate at 3,000 revolutions per minute. The cutting head chews through frozen ground like a blender crushing ice. Behind the cutter, a conveyor system removes soil at 500 cubic yards per hour. But here is the insane part. These machines have ground-penetrating radar built into the cutting head. As they dig, they are scanning 10 feet ahead, identifying buried boulders, ice lenses, and variations in soil density. The AI adjusts cutting speed and depth in real time to avoid damaging the machine or creating an unstable trench. One machine can dig 3 miles of trench per week through permafrost that would take conventional equipment 3 months. In the desert sections, the problem flips. The soil is so loose and dry that trenches collapse almost immediately after you dig them. Sand flows like liquid. You dig a trench in the morning, and by afternoon it is half filled again. Western pipeline projects in sandy terrain use extensive shoring, essentially building temporary walls to hold the trench open. It is slow and labor-intensive. China's solution is speed. Their trenching machines in the desert move at nearly 4 miles per day. The trench barely exists for 6 hours before pipe is laid and backfilled. They are not fighting the sand. They are moving faster than it can flow back. Behind the trencher, a pipe-laying machine follows immediately, lowering sections into the trench within minutes of it being cut. A third machine right behind that backfills and compacts the soil before the walls can collapse. It is a 3-machine ballet moving across the desert at a pace that seems reckless. Except it is working. They are laying pipeline in conditions where Western engineers said you would need to stabilize the ground first, a process that would add years to the timeline. Then they hit the mountains and everything got worse. The Altai Mountains are not just tall, they are geologically young. That means the rock is fractured, unstable, and prone to landslides. You are trying to bury a pipeline on slopes that regularly shed thousands of tons of rock without warning. And you need to cross valleys so deep that suspending the pipe is not an option. It has to go through the mountains, not over them. This means tunneling. Miles and miles of tunneling through rock that shifts and cracks. China brought in tunnel boring machines originally designed for their subway projects, but modified for pipeline installation. These machines are 400 feet long and weigh 1,200 tons. The cutting face grinds through fractured mountain rock at 40 feet per day, while simultaneously installing reinforced pipe sections behind it. They are not digging a tunnel and then installing pipe. They are doing both at once. But here is what makes this entire project actually work. You have 6,200 miles of pipe buried across terrain that wants to destroy it. Earthquakes, landslides, temperature swings that range 190 degrees. Any one of these could cause a rupture that turns this into a useless steel tube. China embedded fiber-optic cables directly into the pipe walls during manufacturing. Every single inch of this pipeline is monitored in real time. The fiber optics detect temperature changes, pressure variations, ground movement, even acoustic signatures of developing cracks. 4 billion data points per second across the entire length. The AI system processing this data does not just monitor, it predicts. It learns the normal patterns of every section. When something abnormal happens, automated valve stations positioned every 30 miles isolate problem sections in under 90 seconds. If the AI detects a developing crack, it reduces pressure before the crack can spread. If it senses ground movement indicating a landslide, it reroutes flow before the pipe is touched. This isn't just a pipeline, it's a living system that adapts in real time. The first 3,000 miles went live in October 2024, delivering 30 billion cubic meters of natural gas annually. The remaining sections finish in late 2025, 2 years ahead of schedule. When fully operational, this pipeline will move 100 billion cubic meters of gas per year through terrain every Western engineer said was impossible to cross. They built it in 4 years using technology that did not exist when the project started. The robots that welded it, the AI that monitors it, and the steel that composes it were all developed specifically because existing solutions were not good enough. You just watched China build the world's largest oil and gas pipeline through conditions that would break any conventional system. And they did it faster than anyone thought possible.